This video is for Math 0232-1332, and this is going to cover sections 10.1 and 10.2. 10.1 is about probability. This is a topic that's covered in a lot of different math classes, and it goes way back to even junior high times. They do probability questions on junior high standardized testing. Many people have experienced it in their lifetime if you play card or dice games or follow sports statistics and find probabilities of things. So some students have good background knowledge with this, others have seen it briefly, and sometimes it takes a little practice if you haven't had too much experience with probability before. But the basic idea behind it is you take how many good things can happen to you, you count up the number of total good things that can happen, and you divide by the total number of ways it can happen. Good divided by total. A real basic one is probability of flipping a coin and getting a heads. So this is a shorthand way of writing probability of a heads. Well, a coin has two total sides, so the bottom's 2, and there's one good thing if you want to get a heads, so it's 1 out of 2. And sometimes they'll change it to a decimal or a percentage, but 1 out of 2 is good enough. If you roll a die, roll a single die. Die is singular, dice is plural. If you roll one die, you're going to get a 1, a 2, a 3, a 4, a 5, or a 6. When you list everything that can happen to you in a probability experiment, this is called the sample space. The sample space gives you a listing of everything that can happen. In some cases, it's too hard to write the whole sample space down, but if you can write it down, then you could at least look at it, and it gives you probability answers right away. I can clearly see there are 1, 2, 3, 4, 5, 6 things here. So the probability of rolling, let's say, a 3, only one of these 6 numbers is a 3, so that's my only good case right there. So the probability of rolling a 3 is 1 out of 6. Where I'm doing good over total. In theory, it's 1 out of 6. Before I go to roll it, I would say there's a 1 out of 6 probability of rolling a 3. But when you actually physically take a die out and start rolling it, in any one roll of the any attempt of the experiment, it's not like this is guaranteed to happen. So it's just my chance of doing it. I have a 1 out of 3 chance in theory of this happening. This is what's called classical probability. It goes back hundreds of years when gamblers were trying to figure out ways to get edges over other people. And classical or theoretical probability, in theory, there's a 1 out of 6 chance that I'll roll a 3. If I were to actually pick up a die and roll it 6 times, it's not a guarantee that one of the 6 times will be a 3. So if you roll a die 6 times, or you roll a die 100 times, or whatever, any kind of a sample that you actually take, that's what's called empirical probability. Empirical probability comes from rolling it and doing a sample of it. And if your sample size is large enough, then empirical probabilities are really close to the theoretical ones. But if you have a small sample size, they can be quite different, actually. If I roll a die 6 times, I might not get any 3s, or I might get 1 3, or I might get 5 3s. So there's no way to know until you actually do the experiment. And that's what they're talking about here in this very first problem of section 10.1. 10.1 is basic concepts of probability. It says explain the difference between theoretical and empirical probability. Empirical probabilities are coming from samples if I actually sit down and roll the die. If I roll a die 6 times, I may or may not get 1 out of 6 of them to come up as a 3. They're calculated using experimental data. You have to actually do an experiment to figure out empirical probabilities. In theoretical probability, we assume all outcomes in the sample space are equally likely outcomes. And that's why on this die problem right here, with rolling one die, actually the probability of a 1 is 1 out of 6, because only one side has a 1. The probability of a 2 is 1 out of 6, and so on. Probability of a 3 is 1 out of 6. Probability of a 4 is 1 out of 6. Every outcome has an equal chance of occurring, so every outcome that can happen is equally likely, they call that. And that's what happens in theory. In theory, they're all equally likely. But in practice, if I actually do an experiment and I actually roll the dice, I don't always get equal amounts of every possibility, especially if you do low amounts of rolling. So the reason we have empirical probabilities is because we normally have to do an experiment to see what's going on. And then you can actually estimate theoretical probabilities if you do large enough samples. Decide whether the statement is true or false. An event is the result of a single trial of a probability experiment, whereas an outcome is any subset of the sample space and could include more than one event. This is false because it's backwards. An outcome is a single trial. An outcome is a single trial. So if you roll a die, whatever happens is called an outcome. Single, what they call it, a single result, single trial. You can roll a die and try to get a 1, 2, 3, 4, 5, or 6. An event can be any single outcome or group of outcomes. So this can be one or more outcomes. In fact, an easy example of an event that's not just one thing is roll a die and try to get an odd number. The probability of an odd number is an event, but it consists of 3 outcomes because there are 3 odd numbers on a die. There's the probability of a 1, a 3, or a 5. So an outcome is any one of these 3, but if I put all 3 of them together and say I'm trying to get an odd number, now I have an event because I have multiple outcomes going on at once. Express the answer in simplest form. If a die is rolled 1 time, see that's the example I was already doing. If a die is rolled 1 time, find the probability of getting a 6. Well, there's only one side that has a 6, so this is 1 out of 6, literally. And students on tests often forget to put the 6 in the denominator. They'll just tell us how many times it can happen. And if you forget the denominator, not only is the answer wrong, sometimes it's an impossible answer. Here's kind of similar to the example I was doing. Try to get an even number. Well, a die has 6 total sides. So the sample space tells you your denominator. A single die has 6 sides. How many of them are even? There's 2, 4, and 6. So the probability, turns out probability of evens and odds are both the same, because this is the probability of a 2, 4, or 6. So both of these are 3 out of 6. And this is why in Las Vegas or other casino areas, if one of these 2 had a better chance of occurring, then everybody who gambles would bet the higher one, and then nobody would ever bet the lower one. So kind of almost in practice, they would need to be the same, otherwise there would be an advantage to betting one of them. Both of these equal a half. Now they said put a simplest form. So if you put 3 out of 6, it's technically equal to the answer, but they count it wrong. So you write your answer in simplest form. So you always have to reduce when you can. 1/2. Both of those divide by 3. So you can at first put this over 6. This is what I always do, is I get my total right away. And this is 5 parts of rolling 1 die. So the total starts off as 6 every time here. And then you go back and count how many good cases are there. And then if you can reduce the fraction, then you do that at the end. So what's the probability of getting a number less than 4? I already know there's 6 sides on a die. There's all 6 of them. How many of these are less than 4? they could ask for less than 4, greater than 4, less than or equal to 4, or greater than or equal to 4. But this one was just less than 4. Less than 4 doesn't include 4, so it's actually just 1, 2, and 3. So this is 3 out of 6 for the second time in a row, which would reduce to 1/2 again. And in gambling games, this is what they call a fair game. Say you and another player are playing, rolling dice against each other and betting money. And one of you says, I'm going to try to roll an even number, and the other one says, I'm going to try to get a number less than 4. You're each doing different events, but because they both have the same probability, then that's what's called a fair game. Each player has a 1/2 chance of winning. That's a fair game. But if your chance of winning is 1/2 and their chance of winning is 1/6, then you have a better chance of winning. And it's not a guarantee you'll win any one time the game's played, but in the long run you would win more. And that's literally how all gambling games are devised and how all casinos in the world operate, is every casino game makes sure that they have a higher probability of winning than any player does. And therefore they win in the long run. And they don't care what happens in the short term. They actually like when people win big amounts of money because it makes other people excited and wanting to play. When you see your friend or some stranger over there screaming and yelling that they want $1 million, then it makes you want to play more. And the more you play, the more people play, the more money the casinos make in the long run. If nobody was ever winning, except in very rare cases, then people wouldn't be so interested in gambling, and then the casinos wouldn't make money either. Now, here are probably 2 extreme cases of probability. Sometimes when you do something in a probability experiment, it either cannot occur or it's guaranteed to happen. This is the best and the worst that can happen. If I roll 1 die and I'm trying to get a number less than 7, it's guaranteed to happen because every number on the die, 1 through 6, they're all less than 7 no matter what I do. So literally what I have is a 6 out of 6 probability of this occurring. There's 6 sides on the die, and if I'm trying to get less than 7, then all 6 of them are good for me. 6 out of 6. Now that reduces to 1. 6, anything divided by itself is 1. So it turns out 1 is the highest probability you can ever get. You can never get higher than 1. On the other side, if they said greater than 7, there are no numbers on a die that are greater than 7. So then you would have a 0 out of 6 or a 0 probability. So it turns out answers to probability, answers to probability questions always have answers between 0 and 1. 0 is the lowest you can ever get. It can't be negative. And 1's the biggest you can ever get. It can't be bigger than 1. Usually it's in between like 1/2 and 1/6, where you're getting like decimals or fractions that are between 0 and 1. But somebody will say on a test, they'll answer a probability question and they'll say it's like 10/3. And they don't realize that's an impossible answer because 10 divided by 3 is 3.333 repeating. And you can't get 10 divided by 3 in probability because it's bigger than 1. So you can't do 10 divided by 3. So just make sure whenever you're answering probability, if it's ever a fractional form, the top of the fraction can't be bigger than the bottom. And it can't be negative, and it can't be bigger than 1 no matter what for a probability answer. Getting a number greater than 2 and an even number, and means they both have to be true. So which numbers are greater than 2, first of all? Numbers greater than 2 are 3, 4, 5, and 6. And how many of those are evens? Only the 4 and the 6. So 4 and 6 are the only 2 numbers on a die that are both even and they're bigger than 2. So there's 2 out of 6 ways to do that. 2 out of 6, which both of those can divide by 2, so it becomes 1 out of 3. And means they both have to be true. Okay, a list contains the names of 6 anthropology students, 3 sociology students, and 4 psychology students. One name is drawn at random, and you're going to assist the professor's new study. Find the probability that the chosen student is an anthropology student. Well, there's 6 of them, so 6. See, people do this on the test all the time. They're like, oh, there's 6 anthropology students, so the answer is 6. Well, it literally can't be 6 because that's bigger than 1. It's not possible for it to be 6 as a final answer to probability. What you're forgetting is the total number of people. There's 6 of this, there's 3 of that, and there's 4 of that. 6 plus 3 plus 4 is 13. So always think of probability as good over total. If you don't put the total, it's not only wrong, it's an impossible answer, actually. It's impossible for probability to have an answer of 6. I get that all the time on tests because I teach this class and then I teach other classes that do probability. One class I teach a lot is statistics, Math 1342. And all the time, students in there, when they do their probability chapter, they always put 6 for an answer, and it's just an impossible answer. A psychology student, well, there are 4 psychology students, but we already know the total's 13. This is why I like to get the total first, because once you know the total, it's the same in every part unless it reduces. But even if it reduces, you should think of it that way first anyway. So this has to be 4 out of 13 before I possibly reduce it. But luckily 13 is a prime number and it doesn't even reduce. So every answer, all 5 of these parts are going to be over 13. Now we saw an and problem earlier. And means they both have to be true, or means either one or both can be true. So I want to count up the anthropology students, count up the sociology students, and of course it has to be over 13 no matter what. So how many anthropology and sociology students are there? There's 6 of the anthropology, there's 3 of the sociology, that's a total of 9. 9 students are either one or the other, and there's a total of 13. Not a psychology student, well, that's definitely over 13. One way to do this is to cover up the psychology students. There are 4 of them. So if you're not one of these 4, then you're one of these other 9. So it turns out part 3 and part 4 are really asking the same question. To say you're not a psychology student means you have to be one of these other 2 because there's only 3 types of students in this sample. Not an anthropology student, so take them out of the equation. There's 13 total students. How many are not in anthropology? If you're not in anthropology, you're either a sociology or a psychology. There's 3 and 4 of them, so that makes 7 out of 13. So there are the first 4. You can't quite see it, but I got green checks. There they are on the first 4. At least the math is easy here. You don't need a fancy calculator to do. I haven't even hardly used a calculator here. And sometimes reducing the fractions gets a little challenging. But we just finished the financial chapter that's very heavily calculator driven. And now this is really just basic math here. If there are only 76 lottery tickets for the big game, one of which is a winning ticket, you buy 13 tickets at random. What is the probability that you will win the super jackpot? So you're buying 13 tickets. That's your good cases. You hope one of these 13 happens. There's 76 total. So 13 out of 76. Now 13 is a prime number, so it only divides by 13. So if 76 divides by 13, then we have to reduce this. But if 76 does not divide by 13, then it doesn't reduce. So does 76 divide by 13 evenly? No, it doesn't. So that means this fraction doesn't reduce. 13 out of 76. In a recent survey reported that 65% of Americans approve of human embryonic stem cell research. If an American is selected at random, find the probability that he or she will disapprove or have no opinion on the issue. So there's actually a handful of types of probability. I don't know if they're going to cover all of them in this class, but The first type of probability is what I call basic or single probability. And it's both, it can be classical or empirical, because those really are the same thing. It's just how are they getting the answers. Basic or single probability is when you do the good over total that we've been doing for a while now. How many good things can happen, and divide by the total. Well, the second kind, there's two ways to do the second kind. The second kind is called a complement. We can write this one as the probability of an event, and I'll just put capital E to stand for any event in general. This is the probability of an event when I do good over total. A complement is when you do the probability that the event does not happen, not the event. It can be found directly with bad over total, basically. So those two problems we had in the last two problems ago, where they said not a psychology student or not a sociology student, I just counted up the other ones. I did the bad over the total, literally. But it also turns out you can find these two answers by using the other one. The probability of an event could be found, instead of doing good over total, you could do 1 minus the probability that it does not happen, if you happen to know that answer already. Or this works too. The probability that an event does not happen is 1 minus the probability that it does happen. And that's often easier to do than to counting up all the bad cases. So say you roll a die, 1 through 6. What's the chance that I don't roll a 1? Well, I could roll a 2, a 3, a 4, a 5, or a 6. I could just count them all up. I could count up all the bad cases, basically. Or I could just do 1 minus 1/6, the chance of getting it. In this problem, there's a 65% chance of the good part of this happening. And 65% is 0.65. So if I do 1 minus 0.65, that'll equal the probability that the event does not happen, which is 0.35. 1 minus 0.65 is 0.35. This doesn't seem so interesting at first, but you'll find later when they get more complicated problems going later in this chapter that this is such a nice rule to work with. Sometimes it's very long and time consuming to figure out all the cases you want, whether they're good or bad cases. So it can sometimes be a lot shorter and easier just to do 1 minus the shorter side of the coin. So you either approve or you disapprove or have no opinion. So the chance that you don't approve is 1 minus the chance that you do approve. Now they want it as a percentage, so I got to change 0.35 back to a percentage, 35%. In a survey, 12% of male college students say they lie sometimes to get a woman to go out on a date with them. If a male college student is chosen at random, find the probability that he does not lie. See, does not. There's a 12% chance that he does. What's the chance that he does not? That's always 1 minus. Now you need to change the 12% to a decimal first. 1 minus 0.12. 0.88, and then you got to change it back to a percentage times 100, 88%. Think of the weather too. If there's a 12% chance of rain, there's an 88% chance it won't rain. And I like to use that example a lot. You'll probably hear me in future sections of this chapter. I'll try to remind you, whenever there's a complement going on, I'll always remind people, if there's a 12% chance of rain, what's the chance it won't rain? And that usually triggers their mind. Oh yeah, that's when I do 1 minus whatever it is. Okay, during a game of gin rummy, which is a card game, Sven needs the 6 of diamonds to make a straight in his hand. He and the other players have been dealt 10 cards each. The other player does not have the card he wants. And all the other cards are in the deck. Okay, what is the probability the next card picked from the deck is the 6 of diamonds? Now, unfortunately, you have to understand cards, and I get students that have never dealt with cards in their whole lives, so then that makes this problem hard to do. Decks of cards have 52 cards in them. There are... Cards have been around for 1,000 years, actually. People have been playing card games for over 1,000 years. Cards have 4 suits. There are hearts, diamonds, clubs. That's kind of like a 4-leaf clover. Hearts, diamonds, clubs, and spades, which is kind of like a shovel. And then each one of them has 13 in them. There's 13 hearts, 13 diamonds, 13 clubs, and 13 spades. And there's an ace. An ace kind of acts like the 1. Ace, 2, 3, all the way to 9. So that's like having 1 through 9 right there. There's a 10. And then there's a jack, a queen, and a king. So there's 13 of them. I don't know, whoever invented cards 1,000 years ago, I don't know why they decided this, but 13 values in each of the 4 suits, so there's 52 total cards. So if you're just trying to get one particular card, normally the probability of any one card is 1 out of 52. There's one card that you're trying to get, and there's 52 total. The only thing is, this card game, the players already have been dealt cards. They've each been given 10 cards. So 20 of the cards are taken out of the deck already, and the card he wants is still in there. So now instead of 1 out of 52, it drops to 1 out of 32, because 20 cards have already been taken out, and his card didn't come out yet. It's still in there. So the 6 of diamonds is one particular card out of the 32 that remain. Normally it would be out of 52, but here it's out of 32 just because they took 20 cards out of the deck. So this problem's not too hard to do if you understand cards, but if you don't even know what a 6 of diamonds is, it makes it a little hard to do this problem. When I make the Alex company makes these problems, and when I do my own homework problems in an in-person class, I try to avoid questions about decks of cards because I get students that have never played with them before, and then they're at a slight disadvantage. Although notice here it says, if you are unfamiliar with playing cards, see this description here. So hopefully if they put this on the test, then you can at least click that during the problem and maybe get help by looking at that. Before cards are dealt for a game of poker, what is the probability that the 31st card in the deck is a queen? It really doesn't matter which card down it is. All 52 cards could be any of the 52. So it could be the first card or the 31st card. Before you deal them, it doesn't matter. If you've already dealt some, it matters, but if you haven't dealt the cards at all, the order of the entire pile does not matter. That's why we shuffle it first. So really all this question is asking is, what's the chance of getting a queen anywhere in the deck? And there are 4 queens, because there's a queen in all 4 of the suits. There's 4 queens, and there's 52 total cards. But that both of those divide by 4, so 52 divided by 4 is the 13 that there's of every suit. And then 4 divided by 4 is 1, so there's a 1 out of 13 chance to get a queen at any point. So that was before the cards were dealt, before the cards are dealt. Now they say 5 cards have already been dealt to each of 6 players. 5 cards have been dealt to each of 6 players, so they've taken 30 cards out of the deck already. 3 queens among those have been dealt. So 3 of the 30 cards dealt out are queens, but there's still 1 queen left then. What's the probability the 31st card in the deck is a queen? So there's 1 queen left. That's the good case. And since they dealt 30 of the 52, there's only 22 cards left. So it's 1 out of 22. Okay, at least you're done with cards now. On one college campus with 5,900 students, 24% are first year students, 29% are sophomores, 28 are juniors, the rest are seniors. If a student is randomly chosen from the campus phone book to win a $500 gift card from the bookstore, find these probabilities. We want the probability that the student isn't a first year student. See that you could add up the sophomores, the juniors, and the seniors, but the problem is you don't even know the seniors. They didn't even tell us that one. So you'd even have to figure that out first. This is a perfect example of doing this complement rule right here. I know that 24% of them are first year students. So the chance that you don't get a first year student is literally 1 minus 0.24. 0.76. That's easier than adding the other three together, even if you knew the third one. So if you want to do this problem directly, you can, but you have to add 29% plus 28% plus figure out how many seniors there are and add that to it as well. That's 4 things you have to do. This is one thing. 1 minus 0.24 is 0.76. I don't see the percent symbol here, so I think they want this left as a decimal. Yes. So only change it back to a percent if the percent symbol is waiting in the answer box. The student is a junior. See, that's just a basic or single probability. All I want are juniors, and I know 28% are juniors. So 28% is 0.28. And in essence, I'm doing the total at the same time because 28% literally means 28 out of 100. So I am still doing a good over a total here, even though it doesn't seem like it. 28 divided by 100 is 0.28. But it is still good over total. And notice the answer is a decimal between 0 and 1 also. And the student is a senior or a sophomore, so the problem is I don't know the seniors right now. But all 4 grades have to add up to 100%. So one thing I could do is I could add the 24% that are 0.24 are freshmen, plus 0.29 are sophomores, plus 0.28 are juniors. That's 81% right there. So if you do 1 minus 0.81, this is how many must be seniors. And so I had to figure that out this time. I could have done that on part 1, but it was easier to do part 1 a different way. But now I don't have a choice because I need to add the seniors. The seniors and the sophomores get added. Whenever it's an or, you're adding things together. Seniors or sophomores, I didn't know how many seniors there was until I did that. But there are 19% seniors, and the sophomores were 29%. So now you can add the 19 with the 0.29 and get a total of 48% for seniors or sophomores. Usually the problem would tell you how many seniors there were, but here they made me figure it out. Okay, in a certain year, Congress began debating a new health care bill. If only they would do that now, but a poll of 1,000 Americans at the time indicated that 438 opposed the bill, 295 favored the bill, and 267 were not sure. You assume you ask a randomly selected American, what is the probability the randomly selected American was in favor of the bill? So this is just good over total, literally. There's 295 that favor the bill. There are 1,000 total. I don't think they'll put a fraction here, but it's literally 295. That's how many good cases there are out of the 1,000 people total asked. So this probably needs to be a decimal, 0.295. Because see, if I click this, there's no like fraction bar or tool button to pick, so that's why I knew that it must be a fraction. I mean, must be a decimal. 0.295. What is the probability a randomly selected American was not in support of the bill? You would not be in support of the bill if you were against it or if you had no opinion of it. So you can either add those two together, or you could do 1 minus the part 1 answer. The part 2 answer is literally the complement of the part 1 answer. So the easier way to do it is literally 1 minus the answer you just got. Or I could take the other two and add them together if I wanted to. So 0.705. So that complement helps so much. Just 1 minus, you can get it real quickly. Okay, here we have men and women, the two genders, and then we can agree or disagree on some issue. And we can be not sure as well. If a person who participated in the survey is selected, what is the probability they disagreed? Okay, the one issue here is these are what I call chart problems. And you need to know the totals here. And they're not given. Sometimes they give you that, but here they're not. Agree, disagree, or no opinion. So the chart's got 975 males who agree. There are 744 women who agree. 166 men disagree. 383 women disagree. 69 and 83. So when I see a problem with a chart like this and there's no totals given, then I like to add the totals before I try to figure anything out. So add the 975 plus the 744. There are 1719 people who agree with this question. Now add this 166 with the 383. 549 disagree. 69 plus 83 had no opinion, 152. If you add all three of these together, 152 plus 549 plus 1719, there are 2,420 people in the survey. That's your total. This is the grand total right here. So any question they ask me, no matter how many parts there are, it has to be something over this grand total. Now, I can add the men, too. There are 975 men that agreed, plus 166 that disagreed, plus 69 that had no opinion. There are 1210 men in the survey. For the women, it's 744 plus 383 plus 83. 1210 for them. 1210 plus 1210, notice that you get the same grand total of 2,420. That has to be true. This is 2,420, this is 2,420. Just use that as a double check. Because if it doesn't add up the same both ways, then you made some kind of misadding or mental mistake that I often do too. So we need this to be over 2,420, and apparently they don't want a fraction here, they must want a decimal. What is the probability that they disagreed? Well, the disagreeds could be the men or the women. There's a total of 549 people who disagreed. So this is still good over total, but they're not going to let me leave it as a fraction when it's such a large fraction like this. Plus, maybe this could reduce it. It would be hard to know that. But I'm literally doing good over total. There are 549 good cases of, because I'm interested in who disagreed with this. Maybe I disagree too, and I'm looking for the people that agree with me. So 549 divided by 2420, that's literally good over total right there. And now, I'm not sure how far they want it rounded. Round to 2 decimal places. So it would be 0.22, but there's a 6 after that, so make it 0.23. So about 23% disagree. What's the probability a person is a man who either agreed or disagreed? A man who disagreed or agreed. So we're talking about these two categories right there. There are 975 men who agreed. There's 166 men who disagreed. So those are the men who agreed or disagreed, not the men who had no opinion. So if you add those two together, that's 1141 but it has to be over the grand total no matter what. See, if you try to put the answer as 1141, that's an impossible answer because it can't be bigger than 1. 1141 divided by 2420 is 0.47. 47% either were agreed or disagreed and were men. Based on the data from the survey, if you had stopped a random woman on the street, what is the probability that the woman would have said that men and women are not paid equally for equal work? Okay, that's weird. Is that what this problem's about? I believe men and women at my company are paid equally. Okay, so the statement is that if you agree with this statement, men and women are paid equally. That's the agree part of this. So what's a chance you stop a woman on the street and she says that men and women are not paid equally? So that means she disagrees with the statement. And it's not that she has no opinion either. She feels that they're not paid equally. So this is all the people who disagree, basically, is what they're saying here. And we actually answered that one already. That was the same answer as this right here, 549 divided by 2420. So it should be the same as the part 1 answer. Just by coincidence, it happens to be the same. So 0.23. Oh no, okay, so I'm doing something wrong. The probability of women said that the men and women are not paid equally. So maybe it does include the ones that aren't sure, because it's the opposite of this statement. Let's try that. So what if it's more than just the disagrees? What if it's the disagrees and the no opinion people? So now I got to add these two numbers together. 549 plus 152. And now divide that by 2420. It's definitely divided by 2420 no matter what. So let's try 0.29 instead of 0.23. Is it 0.29? No, okay. So I am doing something wrong. Let's see if we can see what the answer actually is supposed to be. 0.32. Okay, that's weird. If you stopped a random woman on the street. Okay, maybe it's about the woman. Okay. So what if you only had a woman? So that's what I'm doing wrong, is I'm not, they only want the woman. You want a woman who disagreed. Although that would be too low too. So let's try 383 divided by 1210 maybe. Yeah, that's it. Okay. So what they're doing is that it's out of a woman. So they said a woman was stopped on the street. So that takes all the men out of the equation. So it causes the denominator to be different. It's 1210 instead of the 2420 because you're only dealing with women. And then how many women disagree? That's this 383 right here. This is actually another type of probability called conditional probability, but I guess they just had one part about it. So 383 divided by 1210 is what they wanted us to do in part 3. And that's 0.31, but there's a 6 after that, so 0.32. So go back here real quick and see how the first two problems said if a person who is selected at random. If a person is selected. But in part 3, it's a woman that's selected. So what happened is it narrowed down who we're dealing with. Most of the time, you're dealing with the grand total of the people. But if a man or a woman, if you know you have a man or a woman, then you get one of these side totals instead for the denominator. And then inside that row or column, you want to find it's actually asking about who disagrees with this, but not who disagrees out of all the people. It's who disagrees among the women. Okay, so I had to get that one wrong to see what they were actually doing with it, but if you notice up here now, everything else was correct except 12 was partially correct. I got a green check on part 1 and 2, and I had to miss part 3 to see what they were doing there. But at least when you do this homework, you can do do that one right the first time if you now know how it's done. Okay, so we're done with 10.1. That had 12 problems. 10.2 is called the fundamental counting principle and permutations. Okay, that's weird that they're usually they put permutations and combinations together instead of these two together. Good news is this is pretty easy too, mathematically anyway. Okay, so before we get going on this 10.2, let me give you a magic word here for this video, and we're into a new unit now. This is the fourth and final unit. We do stuff from chapter 10 and 11, but that's all together in one unit. I'm just trying to think of another category to do, so let's do, we'll just do some different months. So let's have the first magic word of unit 4. We'll do the month we're in right now, November. So send me an email with the first magic word of unit 4 is November. A November to remember. Okay, what do we mean by the phrase a permutation of n distinct objects? Okay, before we answer this, let me show you what's going on here. These are called counting techniques. Both this section and the next one's going to continue this too. There are 3 counting techniques, and strangely they're doing the first 2 in section 10.2, and they're saving the third one for section 10.3. The first one's called the fundamental counting principle. This is where you have a series of decisions to make. 2 or more decisions. You have to pick one of these, choose one of these, then choose one of those, and so on. 2 or more of these decisions. This kind of problem is a junior high problem, honestly. And it's done on the STAR test for junior high kids. And the example they get, it's really easy to do. They'll say a kid's trying to get dressed in the morning, and he opens up the closet, and he has to pick 1 out of 5 shirts hanging there, and 1 out of 6 pairs of pants, and 1 out of 4 hats, and 1 out of 3 pairs of shoes, and how many ways can he get dressed? It's a very easy problem to do because all you do is take all the possibilities and multiply them together. I was in Olive Garden one time, and they have this never-ending pasta bowl, like once a year. They do it for a month. And it was just like that. They said choose 1 out of 5 pastas, like fettuccine or thin noodles or regular spaghetti, penne, any different types of pastas like that. And then you could choose 1 of 6 sauces, like Alfredo or marinara or whatever. I don't remember the numbers, but it was something like this. 1 of 5 pastas, 1 of 6 sauces. You could pick 1 of 4 toppings, like meatballs or chicken or shrimp. And then you could choose super salad, 1 of the 2 appetizers. And then how many meals are possible? Literally, you just do 5 times 6 times 4 times 2. It's that easy. That's why they put it on the junior high STAR test. 5 times 6 times 4 times 2, there were 240 meals possible. So these are not probability. You're not doing like what's the probability of something. That's a fraction. This is how many ways can you do something, so then it actually is an integer. It's often a large integer like 240. So the fundamental counting principle, you're choosing 1 of these, 1 of these, 1 of these over and over and over again. But it's always 1 of these, 1 of those. The second type is called a permutation. And you are not choosing 1 of these and 1 of those in a permutation. You have to choose R out of N. So maybe you're in a restaurant and there are 5 main, oh, that's a bad example. Let's do 5 vegetables are available. There's 5 vegetables and you get to pick 2 of them. They let you have 2 instead of just 1. you can choose any 2 of the 5. Like when you get to pick sides, you order a meal and then you get to pick some sides, like 2 sides. 2 out of 5 of the sides you get to have. That's a permutation. I'm not choosing 1 of 2 and 1 of 5. I'm choosing 2 out of 5. That's the difference between a permutation and a fundamental counting principle. And you need to know that difference, because when you're choosing 2 out of 5, you don't do 2 times 5. That's actually the worst thing you can do at that point. So it's not, these problems are not always the easy ones. Sometimes they are, but not always. So a permutation of n distinct objects is an arrangement of those objects, and a permutation order matters. That's the big thing here. In a permutation, order matters. And then when we do next video, we're going to do the combination, is actually the third one, but they're teaching this in a separate section for some weird reason. Combination is very similar to permutation, actually. Order does not matter. So let's say you have a club with 10 people in it, and you want to pick a president, a vice president, and a secretary. I have to choose 3 out of the 10 people to be officers. But order matters because whoever goes first can presumably pick their job, or whoever's first is president maybe. But order matters because the president is a different job than a secretary is. So if order matters, or if the objects are treated differently, not if they're different themselves, but if they're treated differently, then it's a permutation. If order does not matter and you treat people the same, like a jury. In a jury, they pick 12 out of 50 people in a room to be on a jury. They pick 12 out of 50, not 1 of 12 and 1 of 50, but 12 out of 50. But everybody gets an equal job. There is no president of the jury. There's just all 12 people get 1 equal vote. So both permutations and combinations, you're choosing R out of N. That's the first thing you have to decide. Is it choosing 1 of these and 1 of those, or is it R out of N? That tells you whether it's the easy fundamental counting principle from junior high, or is it the more complicated permutation or combination from college. And then once you decide it's a permutation or combination, then it can be hard sometimes to decide, does order matter or not? So then what I look for is, are they treating the objects differently or not? So this is just kind of the definition of a permutation. A permutation is when you select R objects out of N total and order matters, or the objects are treated differently. How does a permutation of N objects differ from a permutation of N objects taken R at a time? I guess a permutation of N objects means you're going to choose all of them. You can do that. You can have 10 people in a club, and I can have them all do 10 different jobs if I want to. So if we want to find the number of permutations of N objects, we use all N of them. And there's a calculation called a factorial for that. If we're only going to take R of them, R is always less than N, apparently, in this definition. Without replacement, we can use, there's a formula that goes like this. Now, this is confusing to people who have never seen this before, so I'll show you this when we start calculating. Okay, so yeah, first we have to understand what a factorial is, see how they're doing these calculations right here. Okay, let me do this one first. The formula behind a permutation involves a concept called a factorial. A factorial is written N for whatever number you want to do, and then they put an exclamation point. So 4 factorial literally means 4 times 3 times 2 times 1. It's 24. 4 times 3 times 2 times 1. I'm looking here. Yeah. Some calculators have it on there as a button. I can type 4 and hit this N factorial button. See, N factorial 4 is 24. So these can get very large very quickly. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. or you can just hit 7 factorial if you have that button. It's 5040. So if you keep going downward, 3 factorial is 3 times 2 times 1, that's 6. 2 factorial is 2 times 1. 1 factorial is literally just 1. The strange one, which is why I skipped it, is 0 factorial. By rule, 0 factorial equals 1, and there's actually a couple of reasons why. But the main reason is sometimes you get these things in fractions like this. And sometimes the denominator has a 0 factorial in it. And in math, if a denominator is 0, the answer doesn't, there is no answer, it's undefined. So by rule, somebody made 0 factorial equal to 1. So I guess we can go back and do this now. 0 factorial is 1 by rule, even if you think it should be 0. But even in here, if I do 0 and hit the factorial button, it does say 1 for that. Let me do 5 before 4. 7 factorial divided by 2 factorial times 5 factorial. You could literally work this out the long way. This is what it literally is. 7 factorial is 7, 6, 5, 4, 3, 2, and 1. And I already figured out that that's 5040. I did that one here on purpose because I knew it was in this homework problem. 2 factorial is 2 times 1. And 5 factorial is 5, 4, 3, 2, 1. You could figure all that out too if you wanted to, but notice here that you can also do this and have the 5 down to 1 can cancel this 5 down to 1. And then I could just do 7 times 6, 42. 2 times 1 is 2, and 42 divided by 2 is 21. I was able to figure this out without a calculator. But you can figure out the whole top, 7 all the way down to 1. Then you could do the whole bottom, 2 times 1 times 5 times 4 times 3 times 2 times 1. You could do this, 240. And then you could divide both of these. 5040 divided by 240. That's 21 that way too. So the good news is there's different ways to do these problems, and if you want to do it quicker or longer than somebody else, there's nothing wrong with that as long as you get the answer right. So this is actually how permutations work by formula. N permutation R is the way we write this. If I want to choose R out of N objects, I want to choose 3 people out of 10 to be officers of a club where order matters. The formula is N factorial over the 2 things subtracted factorial. So if you're trying to do, this is actually 12 factorial, this is actually 12 permutation 2. I can tell by the way the numbers are here. This problem, they're not showing this, but it actually is 12 permutation 2 because they did 12 factorial over 12 minus 2 factorial. And that's 12 factorial over 12 minus 2 is 10 factorial. Now, you can do this out if you want. You can go 12 times 11 times 10 times 9 all the way down to 1, and then in the bottom do 10 times 9 all the way down to 1 and divide the 2 answers if you want to. But it takes it a long time to even do that with a calculator. The nice thing is, look what happens here. 12 all the way down to 1 is what the top is. And the bottom is 10 all the way down to 1. The entire denominator cancels out with most of the numerator. In fact, the only thing left is 12 times 11. And in fact, 12 and 11 are only 2 numbers left, and that's not a coincidence that there's a 2 right here. So you can do 12 times 11 if you want, 132. When I get one of these, what I do is, let me just do a different example. Say you have 23 permutation 4. instead of plugging into the formula, here's a shortcut to doing this. Take the front number 23, then start multiplying by one less over and over and over again, and stop after you have this many numbers. Stop after 4 numbers. So 1, 2, 3, 4. Because everything else will cancel out. Just like the 10 down to 1 here cancels out, the 19 down to 1 is going to cancel out on this problem. So then for me, it's easier just to do 23 times 22 times 21 times 20 to get this answer right. I made this problem up, but that's how you would do that. So 12 permutation 2, the shortcut to doing it is you start at 12, you decrease by 1 until you have just 2 numbers, so stop after 2 numbers, 12 and 11. Now, some of these you can even do this. You can do 12 factorial divided by parenthesis 12 minus 2 parenthesis factorial. And then press equals, and there's 132 that way too. Or I could just type 12 factorial divided by 10 factorial. Whoops. And that equals 132 that way. There's 3 different ways to do this problem. So that's the formula here. N factorial over n minus r factorial. That's the technical formula to do a permutation. But I don't even use this. I just do the shortcut version. It turns out if r is equal to n, usually the r is smaller than the n. In fact, it can never be bigger, but it's usually smaller. So usually you get like 19 permutation 7, for example. If that's what you had, you would do 19. The shortcut would be 19, 18, 17. Keep going until you have 7 numbers. So 1, 2, 3, 4, 5, 6, 7 numbers. That would be the shortcut to doing that problem. But it turns out if you do 6 permutation 6, so this is how many you're choosing out of a total. You can choose 7 people out of a total of 19 to do different things. Or you can choose 6 people to do out of 6 to do the jobs. You can choose all 6 of them if you want to. It turns out that's 6 factorial. Because you would actually do 6 down to 1, because you'd keep going until you had 6 numbers, and it would take you all the way down to 1 to have 6 numbers. So you would start at 6 and you would decrease by 1 until you have 6 numbers, and then you have all 6 of them. So if the 2 numbers are ever the same in a permutation, then it's the same as 6 factorial or n factorial. And the front number can never be smaller. So either the front number is equal to the back number or it's bigger. The front number has to be bigger or equal. If it's equal, then it's just n factorial. That's maybe a shortcut you could do. 6 permutation 2. 3 ways to do this. 6 permutation 2. In my opinion, the easiest way to do it is 6 times 5. Stop after you have 2 numbers. 30. Or you could use the formula and do, it's 6 factorial over 6 minus 2 factorial. And then you could even figure out that 6 minus 2 is 4 and do 6 factorial over 4 factorial. And then do 6, 5, 4, 3, 2, and 1. That's literally 6 factorial there. 4 factorial is 4, 3, 2, and 1. And then you could do the whole top. 6 times 5 times 4 times 3 times 2 times 1 and get 720. Then you could do the whole bottom, 4 times 3 times 2 times 1, which is 24, and divide the two. 720 divided by 24 gives you the same answer of 30 that I got much quicker. Or the third way is you could write it all out and then cancel the entire bottom with most of the top. But there's your 6 times 5 again. So the other 2 ways of doing this take longer, and if you want to do them, you can. But in my opinion, the easiest thing is start at the front number, decrease by 1 until you have as many numbers as the back number is, and then just multiply that all together. That's the easiest way to do a permutation. 8 permutation 8, remember that the shortcut to that is it's automatically 8 factorial. If both of the numbers are the same, it's a factorial of whatever the number is. So that's what number 2 was trying to tell you. 40,320. That on problem number 2, that was this right here, n factorial. They don't say it so well here, but number of permutations of n objects means you're using n and you're choosing all n of them. That's basically trying to say both numbers are the same. Now, 2 permutations 0, here's why. This is exactly why that 0 factorial has an automatic answer of 1. Because if I use the formula for this, it would be 2 factorial over 2 minus 0 factorial. And 2 minus 0 is 2. And anything divided by itself equals 1. So if a permutation ends with a 0, the answer is just automatically 1. Another way of thinking about a permutation is, let me go back to this problem here. Nope, let me go back to 6. Say that you had 6 people in a room and you were going to give away 2 different prizes. I have a $100 gift card to a mall and I have a $25 gift card to Starbucks. I got 6 people in the room. I'm going to put all 6 names in a hat and draw one out at a time until there's 2 winners. The first winner gets to come up and pick what prize they want. Well, even if that person isn't into going to malls, they would probably pick a $100 gift card to the mall over a $25 gift card to Starbucks because it's just more valuable. It's much more valuable. You could always sell it to somebody if you didn't want it, or you could go to the Starbucks in the mall and use it there. So order clearly matters in a case like this if the prizes are much different from each other. That's a permutation. 6 people in a room, 2 are going to win different prizes. There would be 30 ways to do this because you would do 6 times 5. But what if there were 2 people in the room and I had no prizes to give away to them? How many ways can I give no prizes to 2 people? There's one way to do that. I just don't do anything. I keep the prizes myself, basically. So it's a little bit of a technicality, and it might be more logical to say the answer should be no ways to do it. But by rule, this just automatically equals 1. And it's because we don't want to have zeros in denominators. Okay, these counting principles are actually, they could be used in probability, actually. Some probability problems are hard to count. How many good cases there are, how many total are there? Even decks of cards, if you play poker and get 5 cards dealt to you, it turns out there's 2.5 million ways to deal 5 cards out of a deck. It's really hard to count that. So permutations and combinations and even the fundamental counting principle, these are counting techniques that they're basically half of probabilities. They can tell me how many good cases there are or how many total or even both. So maybe I'm doing a permutation to figure out the good cases of a probability problem, and then maybe I'm doing a different permutation to figure out the total number of cases. Then we could divide good by total and get a probability answer. So normally permutation answers are not decimals, but this time it will be because I'm doing 2 of them divided by each other. So number 9, they want me to do 10 permutation 3. That's some big integer number, divided by 23 permutation 2, which is another big, a big integer basically. So I'm just going to calculate both of these, and here's the shortcut in each one of these. This is what I would do if I was doing the problem. 10 permutation 3 is literally 10 times 9 times 8, stop after you have 3 numbers. That's the easiest way to do it. 10 times 9 times 8. I don't need a formula either. 10 times 9 times 8 is 720. That can be a problem all by itself. In fact, the first 8 problems were like that. Normally, you just say 720. It's usually not a fraction or a decimal here. But if I do 2 separate permutations and divide them, then it becomes a probability. 23 permutation 2 is 23 times 22. And stop after 2 numbers. 23 times 22 is 506. Well, I guess this isn't a probability because probability can't have the top be bigger. So this is just some random calculation they're making me do, but it's definitely not a probability because the top can't be bigger than the bottom in a probability, but I can just get some random decimal answer. 1.42 whatever. They'll tell me where to round this. Round to 4 decimals. Okay, 1.4229. This is just a random calculation, but sometimes we do these for probability too. But this is definitely not probability, since probability can't have an answer that's bigger than 1. How many 4-letter passwords can be formed using the letters in the word anxious, if each letter has to be distinct? Okay, so this is a case where I have 1, 2, 3, 4, 5, 6, 7 letters to pick from. There's 7 total letters to choose, and I can't repeat any of them. And I only want to choose 4 of them. I could use all 7, but for some reason you only want a 4-letter password. This is literally a permutation right here. I have 7 total to pick from. Order matters when you're making a word. The spelling of a word matters. A password order matters. If you put the password in backwards, it doesn't work. And I have to choose 4 of them for whatever reason. I could have done all 7, but it can just be 4. So 7 times 6 times 5 times 4. Stop after you have 4 numbers. 1, 2, 3, 4. I stopped after 4 numbers. I didn't stop just because this was a 4, but I had to keep going until there were 4 numbers. It was just a coincidence that it ended at 4. 7 times 6 times 5 times 4. There's 840 different passwords available. See how it's just how many ways can you do it? It's not a fraction or a decimal. And that means if you could do probability, what's the probability that somebody guesses your password? They have a 1 out of 840 chance of guessing your password, which is a pretty low probability, so probably they won't be able to hack your account. How many 4-letter passwords can be formed in the letters in the word anxious if you are allowed to repeat letters? Well, then what happens is every time you go to pick a letter, you have a choice of 7 that you can choose from. So this is not a permutation. This is 7 times 7 times 7 times 7. This is actually the fundamental counting principle. I have to choose 1 of the 7 letters, and then I can choose any one of the 7 letters again because I can repeat. Then I can choose 1 of any of the 7 letters again and 1 of any of the 7 letters again. And you just do 7 times 7 times 7 times 7, or 7 to the 4th power. Then there's 2,401 different passwords instead of 840, so it gives you more password possibilities. Usually on passwords you can repeat things, so normally we don't have this restriction that you can't repeat. 2401. So if you can repeat, it's the fundamental counting principle, but if you can't repeat, then it's a permutation. That was a good problem because they had both cases in the same problem. Out of a group of 9 students on the student government, how many different ways? See, this is my example. President, vice president, and treasurer. I'm going to choose 3 out of 9. See, this is 3 out of 9. I'm not doing 1 of 9 and 1 of 3. Don't do 9 times 3 here. This is not 1 of 9 and 1 of 3. That's the only way you would do 9 times 3. This is choose 3 out of 9. And because it's president, vice president, and treasurer, the jobs are different. I'm treating these people differently. A president is treated differently than a treasurer is. Try telling Donald Trump he's got to be the treasurer today. He would throw a fit because he's got to be the most important person. So this is a clear permutation where order matters and the objects are treated differently. And you always put the bigger number first, smaller number second. This is not 9 times 3. That's the junior high version. This is 9 times 8 times 7. Stop after 3 numbers. There's 504 ways to pick this set of officers. That's a good example of a permutation, actually. How many different ID cards can be made if there are 5 digits on a card and no digit can be used more than once? See, if you can't repeat the digits, that's a permutation. If you can repeat, then it's the fundamental counting principle. So we have different ID cards. If there are 5 digits on a card and no digit can be used more than once, but apparently on this problem, you have 5 digits to pick from, and you're going to use all 5. I got to pick 5 out of 5. And if I can't repeat, that's a permutation. So 5 permutation 5. Remember, if you ever do a permutation where both numbers are the same, that's the same as a factorial. So this is just 5 factorial. I have 5 digits, I can't repeat them, and I have to use all 5. That's 840 ways to do that. But if I can repeat them, then I have to choose one of the 5 digits, choose one of those 5, and choose one of these 5, and choose one of these 5, and I have to do that 5 times because apparently they're making me use all 5 of them. But I could have stopped after 2 or 3 of these too if this wasn't a restriction on this problem. But yeah, this is just 1 of 5 times itself 5 times. This is 5 to the 5th power. You can either do 5 raised to the 5th, 3125, or 5 times 5 times 5 times 5 times 5, 3125. Are we using all of them? How many different ID cards that can be made if the digits can be repeated? Okay, so that's, oh, I did get the first one wrong too. I know it's wrong. It's not the 5, there's not 5 digits to start with is the problem. Digits, if you look on a calculator, see this calculator right here? There's actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different digits. It's 1 through 9 plus 0. So actually what's happening is I'm choosing 5 out of 10 different numbers, not out of 5. It's 5 out of 10. There's 10 total digits to pick from, and I need to pick 5 of them. So the part 1 should be 10 permutation 5, not 5 permutation 5. So it's not a factorial actually. It's 10, 9, 8, stop after you have 5 numbers. So there, 1, 2, 3, 4, 5 numbers. 10, 9, 8, 7, and 6. So the first answer is actually 30,240. And then the second one is you have to pick one of 10 numbers, not one of 5. You're only doing 5 digits, but each time you go to a digit, you have 10 choices to make. And you can repeat, so it's 10 every single time. So every time I get to a slot in my password, I have to pick one of these 10 digits, then I have to pick one of these 10, then one of these 10. This is 10 to the 5th power. So even though we're choosing 5 digits, every digit we choose, there's 10 possibilities. 10 to the 5th power is a 1 with 5 zeros attached to it. It's actually 100,000. How many different ways can 9 types of laser printers be displayed on a shelf in a computer store? So if you put things on a shelf, you could argue, does the order matter or not? If they're on the shelf, does the order really matter? I would say no, but it must matter here because this is the permutation section, and we're going to do combinations in the very next section where order doesn't matter, so we haven't learned that yet. So they didn't say it here, but I'm assuming that the order matters because we haven't learned the case where order doesn't matter. And this is a case where there's 9 laser printers, and it doesn't say it, but I'm assuming that you're putting all 9 of them on the shelf too. So this is where there's 9 total available, and you're using all 9, and apparently the order matters because we haven't learned how do you do the kind when order doesn't matter. See, on this problem, I thought I was using all of them, but I wasn't. I was actually choosing 5, but there were 10 total to pick from. You don't have to use them all, but you can use them all. Here we are using them all, I think. So this one would be 9 factorial then. 9 factorial is 362,880. 362,880. This problem would be harder if it was on a test and it didn't tell me which kind it was. But I could tell here just because we're in the permutations section. We haven't got to the combinations yet. Shanna works at a donut store. Out of, that's a key giveaway that it's not one of these and one of those. Out of 17 contacts in the store's cell phone, how many ways can she set the first 3 speed dial contacts? See, she's choosing 3 out of 17. She's choosing 3 out of 17. She's clearly not using them all. But it's 3 out of 17. It's not 1 of 3 and 1 of 17. If this was like choose 1 of 3 donuts and 1 of 17 drinks or something like that, then you would do 3 times 17. But this is 3 out of 17, so this is either a permutation or combination, and it must be a permutation because we haven't learned combination yet. So the best way to answer this is 17 times 16 times 15 and stop after 3 numbers. Stop after you have 3 numbers. Start at 17, go down by 1 until you have 3 numbers. So 17, 16, 15, stop after 3 numbers. But it's not 17 times 3. So 4,080. So I messed up one problem in this section because I wasn't paying attention to that there was 10 digits available. And I was doing it as if I only had 5. I thought there was like 5 given to me and I had to pick among those 5, but that was wrong. So I do have a green check on everything now, and now we have finished everything in 10.1 and 10.2. 10.1 is basic concepts of probability. 10.2 is the fundamental counting principle and permutations, and then next time 10.3 combinations. The next video will be 10.3 and 10.4 that'll have combinations which are very similar to permutations. So at least that'll be easy. And then tree diagrams, tables, and sample spaces. That one's not too bad either. And we end up doing 6 sections of chapter 10 and 4 sections of chapter 11. So that's a total of 10 sections for the next unit and the 4th and last regular test. Okay, so that is the end of section 10.1 and 10.2 for this first of 5 videos of unit. Actually, it'll be 6 videos because we're going to have to do a review too. So this is the end of the first video of unit 4.